So, chapter 3 is all about graphing these trig functions. So we're going to start by just reminding you guys of some things that we talked about in chapter 1 that'll be of particular use for us throughout this chapter 3. So that is this concept of the parent function and the transformed function. So in chapter 1, we talked about any function, any f of x, can be transformed by, doing a dilation or some kind of reflection or some kind of translation through this function g of x using just these coefficients a, c, h, and k. So this will be particular of interest to us. And then I can get the graph. So that's how I can transform the algebraic representation, the equation. I can transform by doing that. And then the graph, I can take a point from the parent function and then transform it by doing cx plus h, ay plus k. So this is like our equation. And these are two things that will be, or two ideas we'll be using throughout this chapter. So these are two things that you'll definitely want to make sure that you have handy. So that's why we're just kind of recalling them now, so you can write them down in your notes or whatever, so you have them handy again. Because again, it was a little while since chapter 1 that we talked about this stuff. Sergio?
Last year in algebra, when we had like the same formula, we had like 1 over e. Why do we?
I don't know. I didn't. It's just the letter that the person that wrote this part of the textbook used.
Oh, okay.
It wasn't me that did it.
All right.
I don't have a good reason for you. It's just a letter. You want to call it 1 over taco, you can call that variable taco if you want. Pizza slice times f of 1 over taco quantity x minus chicken leg plus sausage. Like lunch. Lunch. That's how you transform a bad dinner into a good dinner, right?
Exactly.
Okay. All right. Well, that was fun, right? I laughed. Okay. So today we're going to kind of do this same idea, but we're going to apply it specifically to these sine and cosine functions. So we're going to start with just kind of an information dump here. So I'm going to just make up like a little bit of a grid, and then we'll kind of fill in the blanks here together. So this is eventually going to turn into a grid. So I'm just starting one column of stuff, and we'll kind of fill this all in together. And some of these words here are probably going to be something that are things that may not be familiar to you. But we'll explain what they mean as we kind of fill them in. Probably would have made more sense for me to build this out as a real table so I could just copy and paste it. But that would have required me to be using my head beforehand, which apparently I'm not going to do today. But my table's not too messy. So I'm going to have, after this column that I've just built, I'm going to have 3 more columns after that. For those of you that are building your own table. If you're not, and you're just like, yo, I'm just going to use whatever you have here, I'm just going to look at the lessons from the book or that are on the content library or whatever, that's fine too, you know. No big deal. Actually, maybe I'll have 4 columns. I guess it doesn't really matter. 3 is enough. So in that last column is both sine, the transformation of sine and cosine. So I'm not going to write both of them out just because it's going to get too long or whatever. I guess I could just take the roof off that and just write it above also, right? We'll just do that. That'll maybe be a little bit more clear. Because I don't really care about all this stuff for that last one. Okay. You guys ready to start filling some stuff in to give you enough grid building time? Okay. So first things first, the domain of sine. If you remember, one of the big accomplishments from last chapter is that we took our definition of sine and moved it outside of the right triangle and onto the unit circle, right? After doing that, we could then take the sine of any angle measure, because the sine was just, the value for sine was related to the position or where the terminal side of your angle intersected the unit circle. And you can do as big or as small angles as you want in standard position. So the domain for sine becomes all real numbers. Is everybody okay with that idea? Just grab the unit circle real quick. Drop that in there because we'll refer to that a couple of times. Right, so for example, if I wanted sine of pi, well, I found pi, that's my input. And 0 would be the value of sine pi, right? Everybody agree? Or if I wanted sine of 8,000 pi, well, that's going to end up being, again, right here. Since it's an even amount of pi's, it's going to be a multiple of 2 pi, right? So the sine output would be something like that, right? And you can, big as you want, it's always going to correspond to some point on the unit circle. Or as small as you want, right? The angle will get as small as you want, just spin in the other direction, no big deal. Everybody's okay with that? Okay. The range for sine is related to the y-coordinates on the unit circle, right? Those are the outputs for sine. The smallest output for sine is going to be the same as the smallest y-coordinate on the unit circle. That's -1. And the largest output for sine is going to be equivalent to the largest y-coordinate on the unit circle. That's just +1. So my range is going to be -1 to +1. Notice that I used brackets here because, well, sine can actually have the value of -1 and it can actually have the value of +1, specifically at pi/2 and 3pi/2, or 90 degrees and 270 degrees, if you prefer degrees, if you're a degree person. At this point, you should be hopefully being kind of comfortable with the radians. You know, we've done a lot with them. Getting there. If you're not, you will be much more after this chapter, because, hate to tell you this, all the graphing we do is really going to be in radians. Here's why, though, from a practical standpoint. If you're graphing, the angle is the x-axis. Do you want to put all the way up to 360 tick marks on a graph? Woof. No, thank you. Would I much rather go up to like 6 point something, like 2 pi? That sounds a lot more doable. That's the majority reason. Yeah, Zach. Of course. Okay. So what the next things we're going to look at are symmetry, continuity, amplitude, etc. Well, let's skip to continuity. That we can do without actually generating a graph yet. Continuity. So the unit circle, regardless of where my terminal side of my angle falls, there's always going to be a point that attaches to it, right? Everybody agree? So there's no discontinuities there, right? Everybody agree? So what do I say about continuity? We'd say this is like everywhere continuous. Go away. So let's generate the graph of sine x here real quick. Actually, let's, where'd that go? Let's do this. That'll make it a little easier to read. Okay. So the graph of sine looks like this. And you're probably going, how in the heck do you get something that looks like this? Well, basically all we're doing is using the unit circle. So the x-coordinate on my graph is going to be the angle measure. And the y-coordinate is going to be the value for sine. So the y-coordinate from the point. So 0, 0 should be a point on my graph. Pi/2, 1 should be a point on my graph. Pi, pi 0 should be a point on my graph. 3pi/2, -1 should be a point on my graph. 2 pi, 0 should be a point on my graph, and I can keep going kind of on like that forever. Yes, sir?
When we get to like graphing them, are those the only 5 you really want to like draw out?
We'll get to that specifically, but yes.
Okay.
Or the only ones you need to generate coordinates for.
Yeah.
Does everybody kind of see what we're doing? We're just pulling points from the unit circle, basically, to plot this thing. Yeah? Is that okay? So let's take a look at this picture now closely. When we talk about symmetry, I notice how like this part of the graph and this part of the graph are identical, right? They're like reflections of each other, right through the origin there. That kind of symmetry was called odd, was the graphical equivalent of odd. So sine is an odd function. Next thing we're going to talk about is the midline. I'm going to go and do amplitude here in a second. The midline is the line, or the imaginary line, that like cuts the graph in half. So there's like an equal area between the graph and the midline, above and below the midline. So in our case, the midline's just the x-axis, because like this area and this area is going to be equal. Everybody's okay with that idea? And since it's going infinitely in either direction, for every up hump, there's a down hump. So there's always going to be like an equal area bounded between the curve and the x-axis. You guys get that idea? Okay. So that midline is the x-axis. I'm going to write it as y equals 0. But I'll write x-axis in next to it. The amplitude is what we'll do next. The amplitude, you can think of two ways. You can either think of it as the distance from midline to maximum or minimum, or you can think about it as half the distance from like a maximum to a minimum. Either way is the same thing. The midline goes halfway through, so still the same. Is that okay with everybody? Okay, so in the case of the sine graph, this distance here between maximum and midline is just 1 unit. Everybody's okay with that? Next up is the period. So notice when you look at the sine graph, I'm going to erase some of this stuff again. You notice that like, hey, if I start here, I have like an up hump, a down hump, and then it starts over again with a new up hump and down hump. And we could keep going on like that forever, right? Everybody kind of see that? A graph that repeats like this we call periodic. And the length of one of these non-repeating segments, so like from here to here, is 1 period. In this case, that's going, the length goes from 0 to 2 pi. So the length there is 2 pi. Feel okay? So nothing, we haven't done any calculation, right? We're just kind of looking at a picture and kind of talking about where that picture comes from. And then like some of the features from looking at the graph. The frequency is basically the number of these periods per like 1 unit of length. So the period and frequency are always going to just be reciprocals. Let's write it this way. Maybe it's going to be a little bit more clear. If my pen wanted to work, pen, there you go. I'll write it that way. Just so we don't think it's 1/2 pi, it's 1/2 pi, right? Okay, let's do the same thing with cosine. So let's generate the cosine graph here right quick, so we can have something to look at. Grab that, and I'll drop it in right here below it. Whoop. So notice that the cosine graph looks pretty similar to the sine graph, but it's not exactly the same, right? Same kind of shape, but they're in kind of a different location. Let's just illustrate how we would get that graph. If I go to my unit circle, same idea as with the sine. So the x-coordinate is going to be my angle measure, and the y-coordinate is going to be the output of cosine. That's going to be the x-coordinate from the unit circle. So 0, 1 would be a point on my cosine graph. And then maybe we take pi over 2 and 0. So that's a point. Pi and -1. That should be a point, and we can kind of keep going on like this as long as we'd like, right? We can just keep spitting them on out. Everybody feel okay about how I would go about generating the cosine graph by hand if I wanted to? I'm not going to ask you to. I just want to make sure that like we get the connection between the unit circle and the graph, because we can keep going around the unit circle. We can keep graphing more as much as we want. We don't want to graph that much though. Okay. So let's go back to filling things out. So the domain for cosine got to be the same as sine, right? The range for cosine was the same as sine, right? Again, basically just going to be the smallest x-coordinate from the unit circle, -1, and the biggest x-coordinate, +1. It's x-coordinates because those are the outputs for cosine theta, right? If I look at the graph, the symmetry, though, is kind of the same on this side as it is on this side, right? The graph looks like a reflection that way. What type of symmetry is that called? Even is correct. And just like sine, cosine also is everywhere continuous. Again, if it's corresponding to just a coordinate from the unit circle, all the coordinates are all there right next to each other. There's going to be never a point where it's going to disconnect. And all these others are going to be the same. The amplitude, still 1. The midline, still y = 0. The period, still 2 pi. The frequency, still 1/2 pi. And I think if you looked at the graph there of cosine, it's here for just a moment. It's pretty obvious that the midline, still right there. The amplitude, still 1. The period, still 2 pi. Right? Everything is still kind of the same. We'll go back and look at the chart there for a minute. I know I wrote that down quick and then I moved it. Okay. What about the transformation? So remember with the transformation, we can reflect across the x or y axis. We can stretch things out vertically or horizontally or shrink them in horizontally. Stretch things out vertically or compress them down vertically, and then move things left or right or up or down. So that's it. That's the only things we can do. Will any of those change the domain? So if x can be any number in, say, sine, and I take any number and I subtract something or multiply it by something, is it still going to be something you can take the sine of? Yeah, right? Because you can take the sine of any number. So it doesn't matter what you do to the original number. You do anything you want, still can take the sine of it. Still going to be good. Does that make sense? You know, if I can take the sine of 35, I can do anything I want to 35, and I can still take the sine of whatever's next, whatever's left. So again, so I do one of these transformations. Can the range change? Yes, right? What two types of transformations are going to change the range? Sergio? The vertical shift and also the vertical stretch, right? So if I stretch it this way, the y-coordinate is going to change by something to do with the a, right? Is that change going to be multiplicative or additive? Multiplicative. Because remember the transformation map that we wrote before, it's a times y. And then if I shift it up or down, it's going to be additive because it's ay plus k. Everybody good with that? So my range now is going to be k minus the absolute value of a, comma, k plus the absolute value of a. Again, I'm using the absolute value of a because a could be positive or negative, and my interval has to be written from small number to big number, so this ensures that I have it written from small to big. That's all. Symmetry, we're not worried about the symmetry with the transformations because it's probably going to destroy the symmetry under most situations. It might not, but a lot of times it will. So there's not really a good predictor. So we're just going to ignore that. If the transformation can't affect the domain, can it affect the continuity? No, right? Think about it this way. With what you can do any of those transformations allow you to like break the graph apart? No, it's still got to stay all connected all the way through, right? If you're stretching and shrinking or shifting or reflecting, like none of that's going to allow you to break a piece off and separate it, which is what you need to do to remove the continuity. Is that a thing?
Yeah, like not one that we.
Well, if the graph was already discontinuous, you could create more discontinuity or denser discontinuity, I guess. But if it was continuous to start with and we're doing just the transformations we're talking about, no. That's why of particular interest in this, why it's beyond, like anything else would kind of be beyond the scope of a high school course. I mean, if you do the right kind of rotation, so like if you allow like a 90-degree rotation, then all of a sudden the domain changes and you have like no longer things that might not be functions or whatever. Or like if you took something that had a horizontal asymptote and you rotated it, now you have a vertical asymptote and you create possibly discontinuity. So like you might be able to like do something screwy with some other type of transformation, like a rotational one, but that's beyond the scope of what we're going to do. Okay. Amplitude, is a transformation going to change this? Yes, potentially, right? It can. What A, C, H, or K is going to change the amplitude?
A.
The A, right? it's going to get taller. That'll create more space in between the midline and it. Everybody agree? Is that change going to be multiplicative or additive? Multiplicative, because it's an A. Since it was, the amplitude was 1 before, 1 times A is still going to be, or is just going to be A. And because we're talking about a distance, and A can be positive or negative, I'm going to call it absolute value A. Again, an amplitude is a distance, so it should be a positive number. Okay. Can a transformation change the midline? Yeah, for sure. Which one is going to change the midline?
The vertical shift.
The vertical shift. So the vertical shift was controlled by K.
Wait, yeah.
K is the horizontal. And is K additive or multiplicative? Additive. So my new midline should just be y equals K. And because you can move up or down, it's just K, right? It doesn't need to be an absolute value. Because it's not talking about a distance, it's talking about a location on the graph. Okay. The period, can that change? Good. What's gonna change it? A horizontal stretch or shrink, which is controlled by C, which is multiplicative. So here it's going to be 2 pi times the absolute value of C. Again, the absolute value there is because C can be positive or negative, but a period is a length, it's a distance, so we need to make sure it's positive. Everybody's cool? And then the frequency is just the reciprocal. So we have something like that. Cool so far? Okay. Let's pause here and do a little example of just making sure that conceptually you got all this stuff. So let's say that our parent function is y equals sine x, and our transformed function is actually, let's do +1 here. Okay. So we're just going to identify the values for A, C, H, and K. We're going to describe like the domain and range and the midline amplitude, period, frequency, and then describe the transformation that's going on relative to the parent function. So we're just going to do, basically just use these vocabs that we've kind of been talking about. Okie dokie? All right. So remember that our parent function in this, or our transformed version in this case, is going to be, or looks like this, right? So before I go out trying to identify my A, C, H, and K, what should I do? Yeah, I got to get that x so it has a leading coefficient of 1, right? I'm going to factor that 1/2 out of there. If I don't do that, I'm not going to be able to correctly identify the H. Oops. Everybody's good with that? When I factor the 1/2 out, I'm dividing each of the things by a half. Dividing by a half is the same as multiplying by 2. Okay. So the A is, in this case, what value? -1/3, very good. The C is what? 2. The h is 6 pi. And the k is 1. Okay. What's the domain going to be here? All real numbers. Easiest question we have for these, right? Doesn't matter what you do to it. Stays the same. What's the range going to be? So remember, it goes k minus absolute value of a to k plus absolute value a. So the k in this case is 1, and the absolute value of a is 1/3. So we have 2/3 to 4/3. Is everybody okay with that? What's the amplitude? 1/3, right? It's just the absolute value of a. So the absolute value of a is just 1/3. What's the midline? It's y equals k. So in this case, it's y equals 1. Should be an equation of a line, not just a number, right? I know what you meant, but I see that frequently where people tell me the midline's a number, and it's like, well, no, not really. It's an equation for a line. So it needs like a y equals on there. I probably would in a course like this, because there is a difference between a line and a number, right? The amplitude's a number. The midline's an equation for a line. So not a lot, but probably a little. Period. How do I find that? Yeah, 2 pi times the absolute value of c. So just 4 pi. And then if I were to describe this transformation in words, what would I say here? Well, since the a is negative, means we're going to reflect across the y-axis. Since the magnitude of a is less than 1, that's going to be a vertical shrink by a factor of 1/3. Since the c is positive, there's no reflection on the x-axis. Oh my goodness. That's the x-axis one. The c is the y-axis one. Eep! Sorry about that, guys. A is x-axis. C is y-axis. My apologies. Serge.
You're not supposed to like follow that order from the first chapter.
Oh, sure. Let's do that then. I don't know. I just got excited.
Does that matter though?
Like if your A's and C's aren't in the right order, I've been deducting for that since they're both multiplicative and they're applying to separate X's and Y variables, so it doesn't really matter too much if the A and C are out of order. But if you did like an H before an A or a C or a K before an A and a C, that I would have made a deduction for. Is basically where I've been at with that. So I've been pretty flexible, but not totally flexible. You know what I mean?
Yeah.
So there we have a horizontal stretch by a factor of 2. And then which we said H has come next, right? So the H is positive, we're going right. 6 pi. And since K is positive, we're going up 1. Maybe I'll write units at the end here. I don't know that that's really necessary, but So not, yes, sir.
So what about the frequency?
Oh, we didn't do the frequency, sure. Remember, the frequency is just the reciprocal of the period, so just 1 over 4 pi. Yes, Emily. Of course. Okay, so this kind of thing is pretty easy, right? You're just basically using these little formulas and definitions and what we did last chapter, or from chapter 1, and just doing the same thing. Amy.
Do we need to memorize that entire chart?
That entire chart. I do. Boy, I don't remember what we've done in the past, to be honest with you. Can you ask me again in a little bit?
Yeah.
And I can look that up and let you know what stuff I gave to you on the test and what I didn't in the past. But I'm gonna tell you right now, like, it's certainly gonna make stuff go way faster doing your homeworks or doing the test if you're not having to look all those things up all the time. But I will definitively tell you one way or the other. I don't want to do it right now. Is that okay?
Yeah.
Yeah, no problem. Again, I'm happy to address that, because I know that's a real concern, right? Like, if I have to memorize all this stuff, I'd rather know sooner or later so I don't have to do it all at the last minute. Totally reasonable. So let's talk about graphing now one of these sine or cosine functions. So to graph one of these, we're going to be transforming points from the parent function into points in our transform functions. Using this transformation map. So the question becomes, what points from the parent function are we going to be using? Well, there's going to be 5 key points from sine, or 5 key points from cosine, that we're going to use every single time. These, I promise you, you will never have to memorize. I would always give these to you. But when you're a crusty old math teacher, you've memorized them all already because you've done this hundreds of times. Or you can pull all of these from the unit circle, right? These are just the quadrantal angles. So just the corners of your unit circle. Not that a circle has corners, but you get it. The maxes and mins on either the x or y direction. So this one is for sine. Sorry, I should have written that. And for cosine, notice the x's are still the same, but the y coordinates are different. And again, this would be something I would not expect you to memorize, but I want to write them all down now so you have them when you go to do the homework. You're not trying to pull these things from the unit circle or whatever. You just have them written down that I've given them to you. I'll put a handout in the content library here in another day or two with the key points in it also, if that'll help. I can do that. It's not a big deal. Type up those bad mama jammas real quick and drop them on in there. Okay. So let's look at an example. So let's say we want to graph let's say I want to graph y equals 2 sine of negative x minus pi over 2 plus 1. So the first thing I'm going to do is make sure that I've written this in the standard transformational form so that I can easily identify my A, C, H, and K. Everybody okay with how I did that? Okay. So now that I've done that, I'm going to go ahead and make my transformation map. So again, that's Cx plus H, Ay plus K. And I'm just going to do that to my key points from sine, because this was the sine graph. Everybody so far so good? So I'll go ahead and show me plugging in the points for the first one, and then I'm going to quit showing that work for the subsequent ones. Mostly just because it's a lot of writing. And it's things I can do in my head arithmetic-wise. So my first point becomes negative pi over 2 comma 1.
Is that actually value next to it between 0?
That's just a parentheses. I'll curve them up for you a little bit. Totally fair question. Again, you can't read it. Makes it hard to understand what's going on later, right? Or even right now, for that matter. Darn it. Where's that snipping tool on OneNote? Does anybody remember where that thing is at? You know what I'm talking about? Screen clipping, that's what I'm looking for. Okay. So I stole this grid from the homework, or from the first worksheet. So this will be like what you're graphing on. It'll look the same as what you're graphing on. So just plot these points. So we have, it looks like every x grid line is a half a pi. You guys notice that? So negative a half pi comma 1 is up here. Oh, I'm going the wrong way. Confound it. You know, Mr. Kulik, sometimes you just... Boogers! Look! Ugh. Ugh. Okay. I don't have one where they're going in the negative direction, do I? I probably don't. No, because Mr. Kulik, you're a bonehead. Oh, I don't want to remake this. I don't want to redo any of this. Nah. All right, this hurts my soul. It's just going to be going the wrong direction, and that is like so infuriating to me, but I just refuse to do anything more editing wise than this right now on the fly. You know, I apologize. And I just got stuff off the grid. It's not my day, guys. That's what I get for just kind of flying by the seat of my pants. It's like, you know, it's like, oh yeah, no big deal. This is easy. I can just make up kind of whatever I want. And like, yeah, you bozo it, and then it won't work out very well.
Mr. Cool, can you write there, just so we know when we're looking back at it, that that's it? Because with my luck, I'll go look at it, and I'll just confuse myself, and I'll forget. Thank you. Perfect.
I can't do much better than that. Katie.
Unless you named Amy.
What's up?
Nice, right?
Oh, of course. Okay. So we've done that, right? What happened here? Oh, this thing shouldn't be here. Oh yeah, that one is. What did I skip? Oh, because it's, oh, good, great googly moogly. It's off the grid. Okay. Okay. So we have like this thing that we've drawn in. But I would prefer that you guys really fill up all the space. So like if we connect these points, we'd have just this much, right? I'm not going to require you show how you get the points. I just want to see like a point with the line going through it where the next ones would be. So we've gone from a minimum to a midline. I should go then up here, and then back to here, and then down to there. Everybody's okay with that? And I'll do the same thing over here. So I was at a maximum, hit the midline. The next one should go to a minimum, and then back to the midline. So I should do like that. Now,
Your midline would be
correct. Yep. Everybody's cool? So once you generate the 5 points numerically, you can just kind of use the pattern of what's going on to fill in the rest of the grid. Everybody's rad with that? No big deal? Again, I apologize for the kooky axes there, but we did some creative problem solving and sorted that out in a way that nobody's probably very happy with, but we acknowledged it. Okay. we feel okay doing this graphing thing? They're all basically the same, right? If you can figure out the A, C, H, and K and manage to fill in and do the arithmetic, it's, not a super complicated process. All right. The next thing we're going to do is talk about going from the graph back to an equation. So let's do one of these. Let me generate one here where you guys can't see it. Looks like a good one. And I'm going to put the grid back on this. Oops. So that it's a little bit easier to tell where the intersections are and stuff. Okay, so here's a graph, and what we want to do is we want to generate the equation from it. So basically we need to sort out and figure out the values for A, C, H, and K. Everybody's okay with that? 4 things. So the first thing I like to find is the midline. So if I look at the graph, it appears the midline is right here at -2. Okay. You're welcome. Why is that great? What's the midline also tell me? It tells me K. The nice part about the K is that it's going to be the same whether you're writing the equation for a sine or a cosine. It's not going to change. Once I have the K, it's relatively easy to figure out the amplitude. In this case, the amplitude has to be just 2. So what does that tell me about the A value? It's 2 or -2. We'll make a decision as to which one we want to use in a moment. Depending on what we want to do, we'll change whether we want to use the positive A or the negative A. We'll talk about how to make that decision in just a moment. Everybody good there? Okay. The next thing I'll do is find my period. So I usually like to go from like extrema to extrema. I think they're the easiest to identify. So we went from -1.5 to +1.5. So the period in this case is 2 pi, right? Went from -1.5 to +0.5. So that's 2 units that we traveled. In this case, their units were pi's, but whatever. Is everybody okay with that? Amy?
And then the pi units are all correct?
Correct. Yes, absolutely. Notice that the y-axis doesn't have pi's on the numbers. Yep, but the x, all of them have pi's on it. So the nice thing about this is this tells me that I can use this to find C. Again, I'm not finding C specifically, I'm finding the absolute value of C. What's up?
Can I see Kate Anderson for 1 minute?
Sure. Okay. So the absolute value of C, again, so C could be +1 or -1. Here's the deal. You can typically take care of any graph by changing the H a little bit and messing with the A and just assuming the C is always positive. That's the way that I like to do things. I think it makes it the easiest Now you can do the same you can find the same problem where the C is negative, you have a different H, and the A would be positive. You could do it that way also. I think that way is a little bit harder. So the way I'm going to show you and the way I'm always going to do that, or do these, is just to fix the C to be positive. And if I do need a negative somewhere, it's just I'll handle it with the A value. Just to give you full disclosure, there are like infinitely many possible answers for a problem like this. But I'm going to always choose to use the C to be a positive one. Okay? Now the tricky part is coming up with the H. So if I'm talking about sine, let's say I'm going to do a sine one, I could write the same answer as a cosine, and I'll do that next. So in the parent function of sine, let's go back and just look at the graph real quick so you guys see what I'm talking about. I'm interested in what happens when the x-coordinate is 0. I'll show you why that particular, when the x is 0, is easiest to use. But that's a midline point. Everybody okay with that? Before the midline point is a minimum, and after that midline point is a maximum. Everybody's okay there? So what I'm going to do is I'm going to, on my graph, find a midline point. Any midline point is fine, and then observe what's happening before and after it. Okay. Oops. So let's say, for example, I'm choosing this midline point. Everybody's okay? So before this was a maximum, and after it was a minimum. So in my parent function, I have, let's write it this way. It was minimum, then my midline point of 0, 0, and then a maximum. In my transformed function, I had a maximum, a midline point of 0, negative 2, and then a minimum. Amy?
So, this is just a clarification. You were saying that you should always use C equals 1. Do you mean that that 1 should always be our value for C, or just in this case, or we should always make it positive?
So I'm always going to pick the positive version of C,
Okay.
is what I'm saying. You can do them where the C is negative, but like it doesn't ever make the problem easier, and I'll often make it a little bit more difficult. So I always just pick it to be C, and then, or C to be the positive, and then just move on about my business with the other stuff. You're welcome. Okay. So the x-coordinate in my transform function point is going to give me my h. And then because these guys are different, that tells me that my a needs to be negative. So my one answer I could write then would be y equals negative 2 sine of 1 times x minus 0 minus 2. That would be a perfectly reasonable answer. Zach?
So how do you figure out that the parent function was minimum, maximum, and the transform maximum?
So I looked at the graph of sine x that we had, that I showed you guys in the very beginning. And if I look at 0, 0, before came a minimum, after it comes a maximum. So that's min, midline, max, if I'm just reading from left to right. Is that cool?
Yeah.
Okay, and if I look at our graph with our transformed function, if I'm using this point, which is 0, -2, before it was a maximum and after it was a minimum. So that's how I just figured it out by looking at the picture.
Okay.
Okay, so this order for the parent function, that's always the same for sine. The order for the transform function will be different, and it could have even been different if I had just picked a different point. Like what if I had used pi -2 instead? So if I use pi -2, we have a minimum, midline point, maximum. So here, they're matching, right? So this would tell me h is pi, and this would tell me that a is positive. So I could have also written this as +2 sine of 1 times x minus pi minus 2. So that would also be a correct answer. Sergio?
Okay with that.
Sure. Lexi?
Can you go over how I got C again?
Yeah. So C, I just looked at the period. So I chose to look at the distance from minimum to minimum. You could go from maximum to maximum, or you could go like midline point to second midline point. Like you have to have midline, midline, and then one more midline to end it. But any of those distances are going to be fine. So this one started at -pi/2 and ended at +pi/2. That's 2 pi of distance. The period is equal to 2 pi times the absolute value of C. So there C just has to be either, or the absolute value of C just had to be 1. Is that okay? And we chose then for C to be +1, but I'm going to make that same choice to choose C to be positive every time, because it's just way less of a hassle. Let's do the cosine version. Again, we could have answered this with a cosine answer. That would have been okay also. Although with the cosine, I'm going to do it's a little bit easier in terms of the h and the k part. So for cosine, let me just do like one of these. My parent function, I'm going to use the cosine point 0, 1. That's a maximum. For my transformed function, I can pick any extreme point that I want. So for example, I could pick this -pi/2, 0. I could pick this +pi/2, -4. I could pick this one. It doesn't matter which one I pick. Let's, for the sake of argument, say I pick this one, -pi/2, 0. That was a maximum. So my h is going to be pi/2. And because these are both maximums, a is 0, or a is positive. Oh, that was at -pi/2, excuse me. what was the AK again? Was that -2? Okay. I just don't want to have to scroll back up. If I had chosen one that was a minimum for my transform point, again, the h is just going to be the x-coordinate, but the a would have to be negative. This is a little bit easier because all I have to do is look at whether I'm using a max or a min. That's all. That feel okay to you guys? So this is decidedly much more difficult than graphing is, right? I just want to take a moment and talk about, before we finish, why I'm choosing every time to use that either 0, 1 or 0, 0 from the parent function, why I always want that x-coordinate to be 0. So just as a little aside, let's say when finding h, why do we want a point from the parent function where x equals 0? Let's just do as an example. So I just showed you that, or I just told you that the x-coordinate was just going to give you the h. Let's write it this way. So we know this is true, right? So if I have 0, 0, and that's going to some cx plus h, ay plus k, that tells me that when I plug 0 in, c times 0 is 0 plus h. So the x-coordinate from your transformed point is going to be h. That's why I can just shortcut to that. If I don't use my parent function point that has an x-coordinate of 0, I actually have to do some algebra. And while it's not difficult algebra, it's like, if I can get away with just doing this so I don't have to do anything, wouldn't you just make a choice to do it so you don't have to do anything? Okay. Let's pause here. We're going to do some more here from going from a graph, or actually next step would be to give you a description and then go to the equation. That's considerably more difficult, but we'll do that